this video, we're going to study the class of polynomial functions. A polynomial function is a function of the following form. We have the sum of terms that look like this, namely we have x raised to a positive integer and then multiplied by a constant. The term that contains x to the highest power is going to be called the leading term of the polynomial, and the corresponding coefficient is going to be called the leading coefficient. The highest power of one such term also determines the degree of the polynomial. So if n in this case is the highest power of the polynomial, then the polynomial will have degree n. Looking at some examples, let's say that we have the function f of x is 2x plus 1. We recognize this as a linear function, but this also happens to be a polynomial. Namely, it is a polynomial of degree 1. So this has degree 1 because x is raised to the highest power of 1. The second function is also a polynomial of, in this case, degree 2, because the highest power that x is raised to is 2. And finally, the last function is a polynomial of degree 17, because x is raised to the highest power of 17, and this 3x to the 17 is the leading term of my polynomial. Polynomials are going to play a very important role in calculus because they have two very important properties. The first property is going to be that of continuity, namely we can draw their graphs without having to jump, and in the case of polynomials that means they're going to be continuous. So polynomials have this really nice property of functions that are continuous, but more so they are also differentiable, meaning their graphs avoid the following problem, namely they avoid having corners or cusps for that matter. So polynomials are nice and smooth, and therefore they will also going to be differentiable because they have smooth graphs. These two properties make them very, very useful in calculus, and you're going to see that we're going to be able to approximate functions of under certain conditions by polynomials, which are very easy to deal with. We are very interested in the end behavior of a polynomial, namely we're interested as x increases towards plus or minus infinity, what happens with the function values. And it turns out that polynomials will either go to negative infinity or to positive infinity, so they have a rather predictable behavior. That behavior is relatively easy to determine simply by looking at the leading term. So let's look at an example. Let's say we have f of x is negative x cubed plus 4x plus 1. We first identify the leading term, that is the term containing x to the highest power, and in this case this happens to be negative x cubed. Now, the general arithmetic with infinity and negative infinity, because they're concepts and not real numbers, can lead into problems. However, in this scenario, the arithmetic works pretty nicely, so this is what we're going to do. We're trying to determine, as x goes to infinity, what happens with the corresponding f of x value. And we have two choices. Is it going to shoot up to plus infinity or down to negative infinity? The way we're going to determine this is by, in quotation, evaluating infinity into the leading term. So I'm going to take the leading term and I'm going to plug infinity, in this case with a positive sign in it, and determine what comes out. Well, infinity cubed is infinity because I only make it bigger, and then because there's a minus in front of it, I have negative infinity. So as x goes to infinity, f of x will go to negative infinity. What does that mean graphically? Well, as x shoots to infinity, after a while the function's going to behave up and down, have maybe some zeros, maybe some turning points, but once after a while it's going to settle down, and then the function graph is going to shoot down towards negative infinity. On the other hand, if x goes to negative infinity, then f of x will do as follows. So we plug, again, we'll look at this leading term, and we're going to plug negative infinity now into it. So I have negative infinity cubed, which gives me negative infinity because the cube does not affect the minus, and minus with minus gives me plus. So f of x will go towards positive infinity. So after a while, once the graph settles down, as x goes to negative infinity, namely in this direction, the polynomial will shoot up to positive infinity. Let's look at another example. Let's say f of x is 3x to the fourth minus a 3x. So as x goes to infinity, we need to evaluate infinity into the leading term. So I'm going to have 3 times infinity to the fourth, which is 3 times infinity, and that gives me infinity. So f of x is going to go to infinity. On the other hand, as x goes to negative infinity, then f of x will go towards 3 times negative infinity to the fourth. Here, because the minus is under an even power, it's going to be turned into a plus. So again, we have 3 times infinity, which is infinity. So both in the cases where x goes to infinity and negative infinity, f of x will go towards infinity. So if I look at the end behavior of this function, again, the behavior in the middle, the function will go sometimes up and down and have some maybe zeros, but towards the end, both arms of the polynomial will shoot up towards plus infinity. I want you to notice that unlike in the case of the previous example, here we had an odd power for the leading term, and therefore the minus here was not affected by this. So we had different end behavior. You look at the graph and one arm is shooting down, one arm is shooting up. However, in this case, where the degree is even, the behavior is the same, namely both arms are shooting up. And that is going to help us match the graph of polynomials to their function rules. That will be one tool, because we know if the leading term has an odd power, then the behavior will be opposite. If the leading term has an even power, then the polynomial will have the same end behavior. So let's use this knowledge about end behavior to match the following functions to their graphs. So I'm giving you 3 graphs of polynomials, and below I'm giving you their function rules. Right from the beginning, we notice that graph 1 and graph 3 have different end behavior, whereas graph 2 has the same end behavior. So I know that graph 2 must correspond to a polynomial of an even degree. So the only polynomial of an even degree is a, the other two are degree 3 and 5. So I know that 2 corresponds to the first function. In fact, checking the end behavior either at infinity or at negative infinity, when I raise them to the power of 4, I will get infinity. So the end behavior does correspond to that graph. So we're okay with this choice. So now we are left with these two graphs, number 1 and 3, and B and C to be matched. So let's look at the end behavior, say, of the last one. As x goes to infinity, we're going to get that f of x will be infinity to the fifth, and that's infinity. And as x goes to negative infinity, I'm going to get that f of x is negative infinity to the fifth, which stays as negative infinity. So I'm looking at a graph that towards infinity shoots up, and towards negative infinity shoots down, and that's exactly what is going on here. Towards positive infinity, as x goes to infinity, the graph shoots to infinity, and towards negative infinity, the graph, the f of x value shoot down towards negative infinity. So I know for sure that this corresponds to choice C. By process of elimination, number 1 corresponds to choice B, and in fact, because there is a minus in front of the x cubed, you will have the opposite end behavior. Finally, let's look at zeros of polynomial and try to understand a little bit about the possible number of zeros that a polynomial of degree n has. Let's recall a quadratic function, namely a polynomial of degree 2. We recall that based on the determinant, this function could have 2 zeros, 1 zeros, or it could also have 0 zeros, namely the graph might not in fact intersect the x-axis, as is the case of this graph over here. So the idea is the degree of the polynomial only determines the maximal number of zeros. In fact, a polynomial of degree 2 can have 0, 1, or 2 zeros. So a polynomial of degree n in general can have, let's record this with at most n real zeros. The graph of a polynomial of degree n, we're now trying to determine the number of local minimum and maximum points. Well, a polynomial of degree 2 will always have one such turning point, a local max or min. So it turns out that the degree again determines at most, because you might not in fact turn, but it might have at most n minus 1. Degree 2 gave me one only point of local max and min, so we have at most n minus 1 points of local max and min for a polynomial of degree n. Looking at an example, let's say that f of x is 5x to the 7th minus 3x cubed plus 2x minus 6. Now, I don't need to try to find the zeros of this polynomial. In fact, it would be very cumbersome, very hard. I would have to use an approximation algorithm, a numerical algorithm of a calculator or a mathematical program, but I can tell you the maximal number of zeros that this polynomial can have. Namely, since this is a polynomial of degree 7, this might have 0, 1, 2, 3, 4, 5, 6, or a maximum number of 7 zeros. Any of these numbers is possible. What this result tells me is that I can have at most 7 zeros for a polynomial of degree 7. Similarly, I can have either 0, 1, 2, 3, 4, 5 or 6 points of local max or min. Namely, I can have at most 7 minus 1, namely 6 points of local max and min. So now let's use all this information and match some graphs to their function rules. So let's consider the following graphs of polynomials and match them to their function rules. So by trying to eliminate some obvious candidates, I noticed that number 3 is a graph of a line. So I'm looking for a polynomial that has a line as a graph, namely a linear function. So that happens to be A. So I immediately know that 3 corresponds to A, and I cut A out because I've eliminated that candidate. Another graph that sticks out is number 2, because it has a very high number of local max and local min, namely 1, 2, 3, and 4. So remember, if a polynomial has degree n, it can have at most n minus 1 local max or min. So this has 4 local max and min, so that means this should have been at least a polynomial of degree 5. It couldn't have been a polynomial still of degree 4, because a polynomial of degree 4 has at most 4 minus 1, 3 local max and min. So let's look. Do we have a polynomial of degree 5 on our list? Yes, there is a polynomial of degree 5, namely h, so 2 is associated with h. What else stands out? Well, I have 6 graphs left, 4 of which have the same end behavior, and 2, namely 5 and 6, have opposite end behavior. So I'm going to be looking to distinguish between these two graphs and their two rules. Of course, they have to be rules f and g, because these have odd degree for the leading term. So let's try to determine this by the end behavior. This one has 2x cubed, so if x goes to infinity, 2x cubed goes to infinity. So I'm dealing with this case here, and as x goes to negative infinity, this term shoots down to negative infinity, so 6 is associated with f, whereas because of that minus over here in front of the 1/3 for the x cubed, I will have the opposite end behavior. As x goes to infinity, negative 1/3 times infinity cubed will be minus, so you notice as x goes to infinity, f of x goes to negative infinity, and when I plug negative infinity into that term, the two minuses cancel and the function values will shoot up to positive infinity. So this happens to be corresponding to g. So I've now eliminated f and g from my graph, and I'm left only with the graphs that have the same end behavior, namely the ones with polynomials that have degree even. Now, looking at the rules, I notice that I'm left with two polynomials of degree 2 and two polynomials of degree 4, so I'm going to treat them separately. Let's first try to identify the polynomials of degree 4. Clearly, this has to be one of them because it's not the graph of a parabola, but also because it has 1, 2, 3 points of local min and max. Therefore, it is the graph of at least the polynomial of degree 4. Also, the graph number 4 is the graph of a polynomial of degree 4 because it cannot be a polynomial of degree 2. We know the graph of that looks like a parabola. So trying to distinguish between these two, namely 1 and 4, and rules C and D, these two of degree 4, I'm going to let the end behavior determine it. So looking at this rule, as x goes to infinity, x to the 4th is infinity to the 4th infinity, and as x goes to negative infinity, negative infinity to the 4th is also positive infinity. So this graph over here has both arms shooting up, and that will be this case over here, and so number 4 corresponds to D, and I've eliminated it, and since I have a minus here, both arms of this graph will shoot down, so 1 will correspond to C, so I've eliminated C as well. Now I'm left between B and E for these last two graphs, 7 and 8, and that's going to easily be determined by the concavity, namely since x squared for E has the coefficient of 1 positive, the graph is going to be concave up, so 7 corresponds to E, and that leaves 8 to correspond to B, which because the coefficient of x squared is negative 2, namely a negative coefficient, I have a concave down graph.